All right, so I'm going to start with doing the like the last example sheet that I gave you guys yesterday. This one, the predicting the position of a proton transfer equilibrium. Um, and did I did I leave this up for long enough for you guys to get this bottom stuff or no? This, the acid with the equilibrium shift right thing. So I know I added this part on the bottom to so I know I added that from yesterday. Uh, so let me start by just saying, like, do you guys know what equilibrium is in general? Yeah, kind of. Yeah, like a balance or a baseline, like or a certain kind of balance between two things or sides or whatever, right? So the reason that the acid base, and I think we mentioned this earlier this year, but the reason the acid base have the um like the sort of half arrows pointing both ways is because when you have an acid base reaction, you actually constantly get um, parts of it ionizing and breaking up and reacting, and then parts of it actually like combining back together. So you get sort of like this, like an equilibrium of the different ions and substances in the acid base reaction. And it depends on how strong or weak your acids and bases are, depending on how much they ionize or stay together, blah, blah, blah. Okay? Um, Now, they do this thing, they talk about the equilibrium shift to one side or another of the equation. And if you try to read it out of the book and stuff, it can be like super confusing. When I first was kind of going through it, it took me a while to figure out what they were trying to say. And very simply, I sort of boiled the concept down to this. It doesn't actually explain all the little nuances that happen, but for right now, for what we're doing, this is totally enough. Very simply put, the equilibrium lies to the opposite side of the stronger acid and base. Okay? So, um, so how does this work? Well, like if we look at this and we use this relative strength chart, okay? What we're going to do is we're going to compare either acids or base because what you'll find is they're the same. In other words, whatever side has the strong acid, that will also have the strong base. So you actually don't have to look at both. I've seen it before as talking about the base, like you look at the base, whichever has the stronger base, but it actually doesn't matter. So, and that's why I've got this labeled here. So if we look, and I'll just show you. So here's the part that you've got to kind of like be aware of though. So HCl is an acid, turns into the conjugate base Cl minus, right? Like that's what this turns into, the conjugate base. But when you compare, you're comparing the acid to the conjugate acid and the base to the conjugate base, not to what it turns into. So we're going to compare HCl and H3O plus, the hydronium ion. So if we look on this chart, we have the hydronium ion is here. Hold on, let me zoom out a little. The hydronium ion is here, and HCl is actually above it right here. So if we look, so the more this goes up this way, it's stronger acids, right? So the higher on the acid list you are, the stronger it is as an acid. So HCl is stronger than hydronium. Everybody follow that? Okay, now just for practice, let's take a look at the base. So water in this case is acting as a base, H2O. The conjugate base is the Cl minus. So if we look those up, H2O, now remember when you're doing the bases, you want to be in the base column, okay? So we got to find water. Water on the base column is right here, H2O, and we want hydroxide on the base column, so that's all the way down here. Okay, now if we look, now be careful because the base goes the opposite way. So the water is, wait a minute. Well, that doesn't work. God bless. All right, now that I'm no longer confused. Okay, so yes, so we are looking at the water, but we're looking at Cl minus as the conjugate base. Oh, I was looking at the right. So the water is a stronger base than the Cl minus one. Okay, good. Makes sense? So both of these, so this is the stronger acid and this is the stronger base. So when you're determining which way the equilibrium shifts, it shifts opposite of the stronger. So in this case, the equilibrium is going to shift to the right, away from the strong towards the weak. Right now, if you want to know like the concept behind why it does this, the simple part, basically the simplest way I can make it is, because these are a strong acid and strong base, they're going to mostly dissociate, which means break up. So most of it is going to turn into this, which means as a balance, you're going to have more of the weak stuff than you will of the strong stuff. So in an acid-base reaction, the equilibrium, you'll almost always have more of the weaker acid and base than you will the stronger, because the stronger ones will react, and the weaker ones won't turn back into the stronger ones because the stronger ones are more reactive. Okay, so this is kind of like weaker also you can kind of think of it a little way as like being more stable, and like the stronger it is, the less stable it is. So it always wants to become more stable, sort of. Okay, so the equilibrium shifts opposite of the strength. Make sense? All right, let's take a look real quick at these. This one. So we're going to use our relative strength sheet to predict the shift. All right. So what we have to do is when they give us just the equation, we have to figure out what the conjugate acid and the conjugate base are, or the acid and the conjugate base, and the base and the conjugate acid. So HSO4 -1 turns into what? Good. So what happened to it? Did it gain or lose a hydrogen? Loss. So if it gives up a hydrogen, that makes it an acid over here. So I'm going to put A under this, and that makes this thing the conjugate base. So I'm just going to put Cb, because they didn't ask us to really write it out. We just need to identify it to figure this out. Which then, as long as we're pretty sure on that, that means our other one has to be base conjugate acid, right? Because we need both. Okay, so now let's just compare. And again, you can do both, but in reality, you only have to check one, because the strong acid and the strong base should both be on the same side. So if we check our acid, HSO4 negative, HSO, not there. Oh, there we go. Thank you. HSO4 negative, and it turns into it doesn't turn into, sorry. We're comparing it to HCO3 negative. So HSO4 negative, anybody see the HCO3? Down here, okay. So the stronger one is the HSO4, correct? So that's stronger, so that means the equilibrium will shift which way? Right. Good. Shifts right.
How do you know if the question is asking you to predict the shift, or is asking like where the equilibrium is? Since it says where the equilibrium lies.
Same thing.
So it's always asking for the shift.
Yeah.
And then Kc greater than 1, that means that.
So this is just the it's like the equilibrium constant, basically, and it'll be like greater than 1 or less than 1. I'm not going to really worry you guys much about that. I'm just putting it in there because they give it to us, and if we use it later, we'll work our way into it. But oops, sorry, can't see that. There we go. Okay, how we feel? All right, makes sense.